Hey everyone, welcome back to my daily coding series. Today is 58. Recently I've been looking at some stack problems, so the last 3 episodes I failed all 3 of these, and since then I've looked at the conceptual parts of the solutions for each of them. I haven't looked at any code, so I think I have a better idea of how to approach them. So I'm going to try implementing what I remember of the conceptual solutions. So we'll start with car fleet. Okay. So I am going to comment all that out. Okay, so this problem, if you didn't watch yesterday's episode, you should, because I'm not gonna go over, or maybe I should. I don't know what I'm doing. All right, so there are n cars. Basically, I'll go over it quickly. So there's position and speed. So it gives you a bunch of cars that all have different positions and speeds. Okay. So there's different position and speed. So for instance, one car might be at position 5 with a speed of 2, and another one might be at, let's say, position 7 with a speed of 1. And you have to figure out like when they intersect. So let's say this car starts at 5 and has a speed of 2, and this one starts at 7 but has a speed of 1. So if they intersect, so if you imagine you have two cars, just a little quick visual demonstration. So if we have two cars, and this one's going like really fast and this one's going like really slow, obviously this car can't pass it, so it will become a fleet where it just kind of like goes the same speed as this one. So if we represent this in a graph, this would be the fast orange car. So it goes until it intersects with this. This is the red car, and then they just kind of go at the same speed because the orange car can never pass it. So the orange car will just continue to go that way. So we're given positions and speeds of several cars, of n cars, and we have to figure out the number of fleets that occur after like a target number of miles, so 10 miles or something like that. Okay. So let's look at one example. So if we have 4, so the positions will be 4, 1, 0, 7, and the speed in this example is 2, 2, 1, 1. So each of these are cars, each column. And the target is 10, so that basically means the experiment will run until 10 miles. So from 0 to 10 miles. Okay, so this car, I'll give them each colors, I guess. So red, orange, yellow, green. So the red car, and then I'll just make a little chart, a little graph. Very useful tool. All right, so if we have position 4, so let's say like this is about 4, and it's going at a slope of 2. So let's say like this is a slope of 2, right? So it looks like that. We have another car, the orange car, at position 1. So let's say that's about here. And it's going at a slope of 2 as well. So it'll be sort of parallel. All right. We have yellow, which is starts at position 0 and has a slope of 1. So like that. Then we have green, which starts at position 7, which is up here and has a slope of 1, like that. So we have to figure out by 10, so if like this is 10 up here, it'd probably be a little bit higher, how many fleets are there? So visually looking at it, we can see that this one will never catch up. So these two are parallel, yellow and green, so they'll never catch up. But we will see that these will catch up to green. But the question is, does it happen before time equals 10? So this is 10 up here. So we can calculate it using simple algebra because these are basically just lines. So the question is, so we can ask ourselves, what time will the green car reach 10? Okay, so let's think. So it's y-intercept, so if we have y equals mx plus b, I'll write it here for clarity. This is the slope of a line. Okay, so 10, so we're wondering when does y equal 10? We know the slope is 1. The slope is 1, so just x, and then the y-intercept is 7. So we can solve this, and x equals 3. So what that means is, this is how many units of time. I think it's hours. Let's just check. It's not really important. Miles per hour, yeah. So, all right. So this is how many hours it'll take. So it'll take 3 hours to get to 10. So we'd say t equals 3 right here. If we look at the red line, red, so when does red get 10? So now I'm going over here. It's equal to 2x plus 4. So we can do 6 equals 2x, x equals 3. So it will arrive at 10 at the same time. So that means they will be one fleet. So these are one fleet. They'll become one car, basically. All right, so now let's look at, orange. I'm just kind of doing them out of order. So orange will arrive at so position is 1 plus 2x. So 2x plus, it starts at position 1. So this will be equal to 4.5. So after 4.5 hours, it'll get there. And then yellow, 10 equals, its speed is 1 plus 0 y-intercept. So x equals 10. So this will get to the target at 10. So we can see that these two arrive at the same points. This one arrives at 4.5. So that means it won't catch up to them. It won't catch up to them before 10 because it takes it too much time to get there. And this one also won't. So my answer based on this would be that there are 3 fleets. And I really hope that's right. Yeah, okay, 3 fleets. So we can kind of use that logic. We can use that logic for sure. So I don't know which one we should start with. I don't remember. But that's kind of the idea is, I guess we could just start from the front, or do we not? I mean, I think we want to start with the slowest one, because the slow ones have to catch up. Like in this case, we start with the one with the highest y-intercept because it starts ahead of the race. Yeah, and then we'll just store which. So I think in the solution I watched, they stored these as tuples, which makes a lot more sense. So I'll probably just do that. So I'll say cars. Okay, so I'm going to define a tuples. Sorry, I'm going to define a list of tuples where each tuple is a car, and each car is a position and a speed. So we'll say cars is a list of tuples. So we'll use list comprehension. So we'll say position of I and speed of I for I in range length of position. So we know that position and speed must have the same length, so we will make a tuple. So if I print cars and return, this should give me what I'm looking for. I just want to verify that. Yeah, so 1, 3, and 4, 2. So then I want to sort cars because I want to start with the one with the highest y-intercept. So if we look here, we have a car at position 0 with a speed of 1. Yep, that's the yellow line. 1 with 2, that's orange. 4 with 2, that's red. And then this is green. So I'm going to do this in reverse order. I think I can do that. May not be able to do that though. Yeah, okay, perfect. So if I pass this parameter reverse equals true, then it will sort it in reversed, a reversed list here. Okay, so I'm going to start with this. So what time does this car, so we'll say for car in cars, so I'll say arrival time. So it's going to be the target. So this is where we basically just solve for x. So what steps do we take? So if we have, let's say, y equals mx plus b, and we want to solve for x, we say y minus b divided by m. So we'll say targets minus, I'll say like position and speed, minus the car's position, divided by its speed. So this is when it will arrive. So now what we do is, so we want to store that information somewhere. So for instance, we'd look at this one, we say, okay, this arrives at time equals 3. If the next car, yeah, so there's two cases. So let's say this arrives at time equals 3, the green, right? It arrives at time equals 3. So there's two cases. Either this car catches up to that and it arrives at a time before 3, or it doesn't. If it doesn't, none of these cars can catch up to this first car, because they will instead catch up with the second car. And that has to necessarily be true because we're starting with the highest y-intercept. So, so let's just store like previous arrival time, I guess. So previous arrival time, and we'll set, so we want to check if basically, like, is my arrival time less than previous arrival time? So if arrival time is less than previous arrival time, and this will set to just infinity because it should always be true for the first one. Okay, so if it's less than, then we know, okay, so we could set the car fleets equal to the length of position. So I'm thinking, so we start out as 4 distinct fleets. And then when this one arrives, we now have 3 fleets. Also, we don't want to update the previous arrival time. Well, I guess we do. We want the arrival time to be, we only want to update it we don't want it to update for the first one though. So maybe we'll set it to negative infinity. Okay, I think this might work. So the first one will always be, this will never be true. So we should never decrease the amount of car fleets for the first one. Otherwise, we'll set previous arrival time equal to arrival time. So like the previous arrival time now is 3. And then when it goes again, we'll calculate it for the next car. Is it less than 3? If it is, it joins it as a fleet. And we still keep track of that the old arrival time. Okay, so we'll return car fleets. I don't know how this is going to work with duplicates or with if we have 0 speed, because we're going to divide by 0. Okay, so it didn't even work for these, so my output was 4. If it's equal to, if they arrive at the same time, then we also should count that. Okay, so that was the issue. So divide by 0 error. Nope. Okay. So that worked. Can't the speeds be 0? If the speeds are 0, then I should be getting an error. So even though it got accepted, I still want to handle that edge case. Well, yeah. The speeds are 0. Like, what if I said speed equals 1, 1? What if I set all the speeds to 0? Then this would surely give me a division by 0 error, right? Yeah. Okay, so I guess none of the test cases have... let me see if LeetCode is like that, because I have a feeling... I mean, if it works on LeetCode, then maybe I'll just call it. It would be a good thing to figure out how to program, though. Okay, so let's see if it works on LeetCode. That's all my old code. I'll just delete that. All right, let's see how this does. There's been a networking error, guys. Copy the code. No. I must log in or sign up to submit. All right, give me 1 second. Yeah, I think I'll just, if it works on LeetCode, I will probably not think about how to do the zeros because I want to get to other problems this episode. But it would definitely be a good like thought experiment for sure. Okay, yeah, looks really good. Yeah, but I don't know. All right, so I guess it does. This one say 0? Was it just an error? No, it says it. Oh, did I miss it? It says greater than 0. Oh, okay. All right, we're good. We're good. There can't be 0 speed. Okay, perfect. So this one's good. So in his explanation, the guy who made the website, he said that you could use a stack, but I don't think you really need to. You can just do it like this. You just need one variable. Okay. All right, so that's one. We're looking at 18 minutes. Wow, that feels like it's been shorter than that. Okay, so let's look again. Stack problems. So generate parentheses I couldn't even solve, but I thought of a way of doing it that, so I didn't even look at the solution for this one. But I was just like, why don't I generate every possible string of parentheses and then just do the valid parentheses check for each one? So I'm just going to do that. So we'll have a function, I'll call it DFS. We're basically going to have a tree. All right, I muted for a second. So we're basically going to have a tree. So it starts with empty string. And then we're either going to add a left parenthesis or a right parenthesis. And we're just going to keep doing that. until the string length is n times 2, because we're given n pairs. So so what could we call it? I guess s. So if length of s is greater than or equal to n times 2, then we will check. So I'll have another function called check valid parens. So we'll check if, I'm just actually going to call it valid parens. If valid parens s, then we'll have a result list. We'll say if they're valid, then append s, and then we will return s. So this is the structure of the code. This is the base case. So if the strings are valid, then we'll just add them to this list, and then we'll return the resulting array. So the time complexity of this is going to be, so to generate all possible parentheses is 2 to the n, and then for every parenthesis that we generate, it will be n, because that's how long it takes to check the valid parentheses. And I was thinking, this n part isn't really that bad compared to the 2 to the n, so it's pretty fine. It's kind of fine to just do it. So that being said, so we'll have a string s. So what we'll do is we will do like the classic backtracking, generate all combinations. So to how you do that is we'll do whatever s is plus a left, and then whatever s is plus a right, and we'll just do that. And that honestly should work. So then we'll call the function dfs with empty string. And okay, valid parentheses. So this problem requires a stack. Is this, before I do that, I just want to make sure if this is good. We also have to return. So we have to return no matter what. Yeah, this is important. And I was thinking of doing these as just one and, but we can't because we need to return always, but only append it if this one is true. So, is it really just this simple? I mean, I guess it is. Also, when I get here, I just want to print s. So I'll say like full parentheses string. What's the singular of parenthesis? I think this is the singular, and this is the plural. Okay, will be s. All right. So let me just do this. So we'll say that all of them are valid. I'm also going to delete all of this. So let me see if this is working before I move on. So the answer will be wrong, but I do want to just check that it's generating all of the yeah, it should have self. Okay, that looks perfect. This also looks great. Yeah, it's definitely going to get pretty costly. I can reduce it very simply. I can reduce it by 2 if I just check that the first character isn't a right parenthesis. There's maybe some shortcuts I can do, but I think that goes against the spirit of the solution. All right, so valid parentheses. So this is a very common problem. It's like the most common stack problem. Here it is. This one, it has all these brackets, but the one I'm gonna do, I should redo this. You don't have to do it that way. The one I'm gonna do is only these parentheses. So we'll say stack equals empty stack for character in string. If the character is an open parenthesis, then we will add it to the stack. Otherwise, I'll just write this function assuming it can only take in the parentheses. I feel like that's bad design. All right, so I'll do or close parentheses. In this case, if now maybe it's not bad design. Okay, so we'll say stack.pop. If stack, otherwise return false, and then return. That's not that readable. All right, so we have empty stack every time we encounter a boom. Every time we encounter an open parenthesis, we're going to append an open parenthesis. It doesn't really have to be an open parenthesis, but so we'll append an open parenthesis. If it's a closed parenthesis, we will pop from the stack if we can. So there must be something. If there's nothing, then we'll return false right away. So for instance, if our string is just a, let's say our string is that, the first character will not be this, so it'll go else. The stack will be empty, so it will return false. And then our stack has to be empty to be valid. So that being said, I think the solution will work. Yeah, all right, perfect. So it's it's a combination problem, so it's going to be slow. But that's just kind of how they have to be, and I should have thought that, like, hey, n doesn't really matter when you're already doing 2 to the n, so I can just check if it's a valid parenthesis. I mean, you can see here it's a super simple algorithm. So this one's called generate parentheses. All right, let's bring it over. Let's see if it works. All right, it's super slow, but that's totally fine. That's kind of what I was thinking. Again, for this one, I'm not really trying to get the most efficient solution ever. I'm just trying to get something that works, because for this one, I couldn't even solve it normally, which isn't good. So yeah, and it's also really memory efficient, so that's that's something. Okay, so I'm at 28 minutes, so I'm going to try to do one more. I don't remember it that much, but I believe I can do it. So this one is called daily temperatures. I think I do remember how to do this one, actually. Okay, so this problem is pretty straightforward, at least in what it's asking. It's also really straightforward to solve in quadratic time, but solving it in linear time is a little bit tricky. I couldn't do it. Okay. So you're basically given a list of temperatures, and you have to return an output list where every element of the output list correlates with the temperature and says, this is how many days until there's a temperature higher than me. So if we look at, we have 30, 38, 30, 60, 36, 35, 40, and 28. So if we look at this, so we have to return an output array. I'll draw it in blue. And it basically just says how many days until there's something bigger than me. So, and if each index is a day. So here 1, we only have to go 1 spot until there's something bigger than you. Here we have to go 1, 2, 3, 4 spots. Here you have to go 1. Here you have to go 2. And you can see the way that I'm doing this is kind of the n squared approach. So I'm just looking, and just a quick note, if there is nothing bigger to the right of you, then you write a 0. So you can see just the way I drew that out was the n squared approach. So for every number, I'm basically counting how many until, there's something bigger than me. So for this one, I go, is this bigger than me? Nope. Is that? Nope. Is that? Nope. Is that? Yes. That's 4 spaces. So that's the n squared approach. I did code that, but you're supposed to try to get it in linear time, which is just O of n. So this one, you can use a stack kind of cleverly. So instead of doing the n squared approach, what you do is you kind of just remember each number that you go to. So for instance, we'll look at 30. So we'll go from left to right. We'll look at 30 and we'll just add it to our stack. So let's say this is our stack here. Then we'll look at 38. So our question is 38 greater than top of our stack? If 38 is bigger than the top of our stack, that means that this, we basically know that the indices, the difference in indices between these two numbers is the answer for whatever index this is at. So in other words, we'd put 1. And then we'd pop it from the stack and we would add 38 to the stack now. And maybe we would store their index as well. Their index. So now 30. So we're asking this question again, but now with 30. So is 30 greater than the top of our stack? No, it's not. So we're going to add it to the stack. And we're not going to do anything else. Now, is 36 greater than the top of our stack? Yes. So we're going to pop whatever's in our stack, and at this index, we're going to put our current index 4 minus that. So we'll put 2 here. I mean 1, because this is at index 3. Sorry, so it's 4 minus 3. So we'll put 1. And then we're going to keep asking this question. So this is really going to be a while loop, I think. I'm kind of just going with my heart here. So we're going to keep asking this question, because what if this was a 31? If this was a 31, then we should get the answer for that. So in this case, 36 is not greater than 38. So we're just going to add it and leave it like that. 35. Is 35 greater? No. So we'll add 35 with a 5. And then we'll go to 40. Is 40 greater than it? Yes. So we'll go to index 5 and we'll take, which index is this? So I'm just going to index them quickly. 1, 2, 3, 4, 5, 6. Okay, so we're going to put at index, this should be, these are off by 1. So this should be 4 and this should be 3. Okay, so we're going to, if it's bigger than, so we look, 40 is bigger than 35. So we're going to pop this element from our stack, and at index 4, this one, we're going to put our current index minus that index, 1. Now we ask this question again. Is 40 greater than the top of our stack? Yes. So at index 3, we'll put 5 minus 3, which is 2. Then we'll pop that. We'll keep asking the question. Is 40 greater than the top of our stack? Yes. So at index 1, we'll put 5 minus 1, which is equal to 4. And then our stack is empty, so we cannot ask this question anymore. So we just put 40 to the top, to the, in our stack. So it's the only element right now. And then once we get to the end, so we'll see 40 is not greater, or 40 was greater than a lot of them. We got to the end. Now 28 is not greater. Once we get to the end, I'm guessing what we'll do is just continuously pop from our stack and set everything to 0. Okay, that sounds good. All right, that sounds good. So a way I could have, yeah, okay. So obviously we're gonna have the while loop somewhere. So while, so let's start with the for loop, I guess. So for temp in temperatures, and then we're also gonna have our stack, of course. And let's enumerate this. That's not how that works. Okay, so we'll enumerate temperatures. So for those of you who don't know, this function basically just returns like an index along with it. So we can say for I and temp and enumerate temperatures. It's basically just like doing a while loop, except sometimes it's a little bit more convenient. So, and here I just want the for loop I want just to run a fixed number of times, and it'll probably be less typing than the while loop because I'll have to do temperatures of I, which is a lot of typing. So I'm just going to do it this way. Okay. So we're going to ask the question. No matter what it is, we're going to add it to the stack at the end. We're going to append the tuple, temp, and I. So we're going to say, while temperature is greater than the top of our stack, the first element of it, we're going to pop from the stack. So what are we going to pop? We're going to pop a tuple. So we can unpack that tuple. So what should we call it? Well, we know it's going to be a temperature and an index. So we could say like T, what is it? It's a previous temperature. So we'll just say previous temp and previous index. Okay. So while temp is greater than the, well, let's say, and the stack has an element in it. So while that's true, what did we do? We popped and then we set the index. So we'll have a result list. So we'll say result of what? The result of what we popped, the result of this equals I minus whatever the index was. Yeah, and I think that's it. And then we'll just always append it. And then we can just return results. Now the problem with this is we're directly indexing result. Oh, what if we set them all to 0 to begin with? 0 times length of temperatures. And then maybe we don't have to do that part at the end I was talking about. Well, maybe we do actually. No, we don't. This should work. Yeah, because it'll just be set to 0. So it won't ever set them, which is fine because we'll just set them to 0. So what I'm saying is like, we'll never set these, but if we just initialize them to 0, then we're totally fine. All right, so that's the third one. So we're looking at 40 minutes. Yeah, this was a great episode. Like I said, I didn't look at any code. I just looked at the solutions, and a lot of that I actually was kind of, I think for a lot of these problems, since I've done a lot of them, it's like, oh, that's the trick, and then I just kind of can scaffold a solution around it. Like for this one, I was like, oh, I don't know if I remember it, but then I was like, oh yeah, we just add to the stack as we go, and then there's like some condition that we check for, and then you can kind of just figure out the rest. yeah, so that's this. Let's check it out on LeetCode. But yeah, so looking at the solutions is important, but I think the biggest takeaway is, what was this one called again? Daily temperatures. The biggest takeaway is probably asking the question, how could I have got the solution by myself? You know, and I think for this one, it probably would be me just thinking like, okay, we need to write these down. And once we encounter something, what information does that tell us about something in the past or something, that we haven't seen yet or something? And just because you could see that the intuitive way to do this problem was the way I did it at the beginning, where you just look at here and then count ahead. So I was solving it like myself n squared, but you can kind of like, take out all the numbers for a second and be like, okay, what do I know so far? And then introduce a 38 and it's like, okay, well, I know 38 is bigger than the last number I just saw. So that means this has to be 1, so maybe that type of thinking of like you yourself as a human, when you solve it, limit your information to 1, like to only what you've seen so far. I think that would be a good way to solve it, because then you're forced to solve it in linear time yourself. So that being said, let's submit this solution. Okay, perfect. A perfectly reasonable solution here. So today was day 58. Thank you guys very much for watching, and I'll see you tomorrow for day 59. Peace.